Hi, I will talk to you today about our work on robust motion in-betweening, in which our system takes arbitrary keyframes of motion and generates the missing motion in the desired time. Here, two keyframes are duplicated and used as only constraints for our in-betweener. My name is Félix Harvé. I'm a PhD candidate at Polytechnique Montreal, a student at Mila, and an intern at Ubisoft La Forge, where I conducted most of this research. I'll talk to you today about why automatic in-betweening is interesting, how to leverage recent motion prediction advances to build a transition generator, and where the naive adaptation to transitions fail. I'll then present how we address those issues through additive latent modifiers before presenting the datasets, experiments, demos, and limitations of our system. So let's jump right ahead into some context. For AAA studios to create ever more immersive experiences, building believable worlds is a key component, in which characters and their movements must be credible. For large games, the required number of different animations needed for a single character is often quite huge, and we always aim at the highest quality possible. For that, two options are usually used: motion capture and keyframe animation, or hand animation. Motion capture offers a great fidelity of human movements, but is very costly and time-consuming due to the infrastructure and pipeline steps required. Keyframe animation is also highly time-consuming, and the obtained quality is often lower than when capturing actor movements through mocap. This is due to the limited tools accessible for keyframe animators that are often based on curve editing. Our goal is to build a data-driven system that can bridge the gap in quality between the approaches while reducing the workload of animators with an automatic motion in-betweener. First, let's see how we start from motion prediction networks. At its core, our architecture is based on deep sequence-to-sequence neural networks commonly used for motion prediction. In this setting, a past context of a few frames is given as input to a model that predicts the next frames of motion. A string of work based on recurrent neural networks have shown good results in such unconstrained cases. In this work, we build a strong motion predictor baseline using different advances from these papers and tackle the task of transition generation, where a target keyframe is given as additional constraint. The model then needs to generate the missing motion that links the given keyframes. More precisely, the model is an autoregressive recurrent neural network that generates one frame at a time, given the current frame, the target frame, and its current hidden state content. We tackled this problem in 2018 in our technical brief on recurrent transition networks, on which we base our core architecture by using the same input separation and related encoders. Namely, we use a state encoder, a target encoder, and an offset encoder. We feed the state encoder the current joint local quaternions for each bone, along the root orientation relative to the last frame of past context. We also give it the root velocity and feed contact state as inputs. The target encoder takes as input the target quaternions to reach, and the offset encoder takes as input the Euclidean distances between the target root position and the current one, as well as between the target quaternions and the current ones. The resulting hidden states are given to the recurrent layer, which also uses its own hidden state as input. The LSTM hidden state is sent to a feed-forward decoder that outputs from a linear layer quaternion velocities, root velocities, and feed contact logits that go through a sigmoid nonlinearity to be treated as probabilities. The resulting velocities are integrated to the previous states to compute reconstruction errors. We also perform quaternion normalization and forward kinematics using the stored bone offsets to compute reconstruction errors on global positions, while we compute binary cross-entropy on feed contacts probabilities. Here's a simplified view of what we call the reconstruction-based transition generator. We also operate in the GAN framework and compute an adversarial loss from two critic networks. We use a short-term and a long-term critic that score sliding windows of 2 frames and 10 frames of motion respectively. We use the least square GAN formulation for our adversarial losses, which in our experiments have shown not only to help generate visually better defined movements, but interestingly they also helped the reconstruction performance of our generator. This leads to a good generator in some contexts, but has some notable limitations. First and most importantly, the lack of temporal information prevents the system to correctly adapt to variable transition lengths. This is needed for an in-betweener tool, where animators should not be constrained to place keyframes at regular intervals. The model, as with many data-driven approaches, is limited by the training data. For each past context in the dataset, a single target keyframe is presented during training. This can limit the generalization to new use cases or keyframe modifications. Finally, this model is deterministic by nature and offers a single fixed transition for a given context. We propose two additive latent modifiers to address these issues. We have found latent modifiers to be useful to force the model to be conditioned on certain constraints. As opposed to using additional inputs, latent modifiers shift the input's representations in the manifold space and effectively modify the behavior of the model. Our first latent modifier is a time-to-arrival embedding, which is applied on all input representations. It is based on the positional encodings used in the popular transformer networks from the natural language processing literature. Transformer networks use positional encodings to give word embeddings a notion of position in the input sentence. In our case, computations of our modifiers are based on the remaining time steps before the target keyframe, or time to arrival. Here's a visual depiction of the TTA embedding. It consists of a dense, continuous code that evolves through time on different frequencies for each of its dimensions. It therefore shifts the input's representations uniquely for every time step, effectively conditioning the recurrent layer on the time to arrival. To avoid initializing the TTA embedding to considerably different values when generalizing to longer sequences, we clamp its values past a certain transition length. This prevents the recurrent hidden states from diverging too much by keeping the input representations in a known manifold region. When compared to using a single additional TTA dimension either on the state inputs or on the LSTM inputs, TTA embeddings lead to better performance and remove the jump that can occur at the end from the transition to the target keyframe. Here's the result of temporal variations made with TTA embeddings using the same keyframes as shown before. Our TTA embedding thus successfully improves the robustness to temporal variations. The other limitations listed previously are addressed through another latent modifier called the scheduled target noise. This scheduled target noise is applied only to the target and offset representations and is sampled once per transition from a spherical zero-centered Gaussian distribution scaled by sigma target, which is an hyperparameter set to 0.5 in our experiments. The schedule comes from a scaling factor, lambda target, that evolves through time so that near the end of the transition, the representations are noise-free. Our target noise schedule is intuitively similar to an agent receiving a distorted view of its long-term target, with his goal becoming clearer as the agent advances towards it. This allows the model to be more robust to target distortions, but also allows one to sample multiple transitions for a given context, as seen here. Noise concatenation, as done sometimes in conditional GANs, doesn't work as the additional inputs are ignored. For our experiments, we used the human 3.6 million dataset commonly used in the motion prediction literature, and we also present our novel high-quality LAFAN1 dataset. In the paper, we validate our motion prediction model baseline on the commonly used benchmark for prediction on human 3.6M. It doesn't incorporate root displacement and also contains many actions ill-suited for long-term predictions or transitions. Indeed, many actions such as smoking, discussing, and phone call contain sporadic movements that are random on long time frames. It contains over 300,000 frames at a rate of 25 frames per second recorded from 7 subjects. Given the limitations of the human 3.6M dataset actions, we extract all walking sequences in order to keep only actions that are better fit for transition generation. This subset contains over 50,000 frames. We also present a novel high-quality dataset called LAFAN1. All actions in this dataset are natural and well suited for long-term transition generation. The data contains root displacement and has close to 500,000 frames at a rate of 30 frames per second. It's recorded from 5 different subjects. We now present our results. In the current video, We use our neural in-betweener in series to reconstruct a validation sequence from which random keyframes were saved. The variation lengths range from 3 to 44 frames, with the network being trained on a maximum length of 30 frames. On the quantitative side, we first build a strong motion prediction baseline that we evaluate on the common Human 3.6M benchmark. We evaluate the commonly used mean angle error as well as the recent normalized power spectrum similarity proposed by Gopalakrishnan et al. As a metric for motion better correlated with human judgment. We first show results of a zero velocity baseline which is surprisingly good on short-term prediction. We then report performance of different short-term and long-term models from Gopalakrishnan et al. The NPSS score is evaluated on their long-term model for 1-second predictions. We also show results of the triangular prism RNN proposed by Chiu et al., who have to our knowledge the best published results for the benchmark. Our motion predictor, that doesn't use yet any target information, shows competitive results on all mean angle error metrics and best results on all NPSS measurements. This confirms our choice of core architecture for transition generation. Note that our ERD QV is based on quaternion velocities as inputs instead of quaternions. Next, we add the target-related inputs and encoders and evaluate our contributions on the Human 3.6M walking subset for in-betweening. We evaluate the model on 3 different metrics for different transition lengths. The L2Q metric is the L2 distance between the generated and ground truth quaternions averaged over all joints and all transition frames. The L2P is the averaged L2 distance over global joint positions. We also evaluate the NPSS metric here. To measure the generalization capabilities of the model, we also measure performances on transition lengths longer than what was seen during training. We first report performance of a simple interpolation technique, which is very good for short-term transitions. We then compare our baseline model, which now has the target-related inputs and encoders, to one that takes regular quaternions as inputs instead of velocities. As this version performs better for longer transitions, we choose this model as our new baseline. This model only uses angular losses. We then go on and add the forward kinematics block to use a positional loss on global positions, which slightly helps. Our TTA embeddings bring the most performance gains across all measures and transition lengths. Our scheduled target noise further improves performances, while most of our best results are obtained when additionally using our adversarial loss. This is interesting as adversarial losses don't explicitly encourage better reconstruction. We further conduct experiments on the larger, more diverse LAFAN1 dataset where we compare interpolation with a reconstruction-based transition generator and with our complete system that incorporates the adversarial loss in our additive latent modifiers. Here, because of the more complex movements, interpolation is surpassed by our transition generators even on very short transitions. All transitions shown in this presentation are produced by our TG-complete model. To qualitatively assess the performance of this model, we embed it in a custom motion builder plugin so it is easy to use in a production scenario. Here is a simple workflow example where walking motion is extended and modified by simply copying and dragging its last keyframe in time and space. The generation of the in-betweening takes less than 2 seconds. The gate can be adjusted by simply moving the target frame and clicking the Generate button again. Then, the animator extends further the sequence with some turning motion using the same keyframe by moving it and rotating it in the scene. The same iteration process is then done by editing the location of the target keyframes. Here is another sequence with other keyframes and an obstacle. We also show multiple samples for the same context. Here are some additional results on more challenging transitions. Although the motion remains realistic, it is hard for the model to continue a perfect one-foot hop. This could potentially be alleviated by providing a longer context before the transition during training. Here, subtle movements are queried and keyframes are shown with spatial offsets for clarity. Since the model learns from real human movements, it is limited by the realism of the conditions it is given. If we take the same 4 keyframes but mirror the second one, an uncommon gait must be performed to make the transition in time, and the model struggles. Sliding back the last 2 keyframes also yields unrealistic conditions not in the dataset, and the in-betweening quality suffers. Finally, asking for superhuman speed by removing the second keyframe and shortening the sequence also fails. Other challenging movements include dancing motions, which are present in our dataset. Here is an example performance obtained when using the whole dataset, compared to when using a dataset where dance motions have been removed, and compared to when using a smaller dataset of dance sequences only. In all cases, it is hard for models to keep the hopping motion going, but combining specialized dance motion with much more generic data significantly helps. To conclude, we aim in this work at bridging the quality gap between mocap and keyframe animation while reducing the workload of animators with automatic motion in-betweening. Indeed, animation authoring is usually resource-intensive and takes time, so reducing the workload of keyframe animation is appealing. Many advances in unconstrained motion prediction can be used, but their naive adaptation to in-betweening is limited. We show benefits of modulating the behavior of such transition generator through additive latent modifiers to address those limitations. We also release the data used to train our model and benchmarking code for future comparisons. There are some limitations to our approach, as we've seen, mainly related to the training data, as it is often the case with machine learning approaches. Also, even though our system allows animators to sample many transitions for a given context, there's no mechanism yet to control the style of the generated motion. This is an interesting future research direction for such systems. Thanks a lot for watching this talk. Here are my co-authors, and check out the paper for more details. Thanks.